Okay, so we pretty much wrapped up this chapter and about titrations. The last thing we're just going to kind of finish up here in this chapter is about indicators, which I think we talked a little bit about. But indicators are really they basically behave like weak acids. They have sort of a protonated form, which is sometimes abbreviated like this guy that has the hydrogen on it. And much like a weak acid, they can dissociate and release that hydrogen and sort of form its basic form of the indicator. And a lot of times, depending on sort of the ratio of the acid that's present, acid form to sort of the basic form of the indicator that's present, as to sort of what color that you would sort of see in solution. Here, typically if sort of the acid part divided by the basic part of the indicator is greater than or equal to 10, we'll sort of see the acid color, while the opposite is true, sort of less than that sort of 10 ratio there, we'll see that base color. But all indicators essentially work, as we talked about, over a specific sort of pH range. They have specific colors in that range. And, the selection of an indicator is really based off of, in most cases for a titration, where you would see your equivalence point. So we did talk about, three types of titrations, really. We talked about, titration of strong acid, strong base, where we would expect at the equivalence point to have just a neutral salt left over, which would mean our equivalence point should be neutral. So we would want, obviously, an indicator somewhere in that pH of 7 range, as opposed to, say, a weak acid strong base titration, which should produce a salt that will go through hydrolysis and will produce hydroxide, and we would expect it to be basic. So we would obviously want an indicator more in that basic range, and as opposed to sort of our weak base strong acid titration that we talked about, where again we would be forming a salt at the equivalence point that will go through hydrolysis and become acidic in that solution. The key to choosing sort of the correct indicator is one where you can obviously visually see a color change occur. The idea of an indicator is usually to tell you, hey, perhaps you should stop at that point. You've kind of reached the equivalence point, and we really want some type of color change to occur at that point. Most of us are familiar with, obviously, the guy down here, which is our phenolphthalein, which is kind of 8.3 to 10-ish. And again, closer to that 8.3-ish range is really colorless. And then it gradually gets into that sort of pink color as we kind of approach 10, and very pink, obviously, at 10. And that's why we use it for a lot of titrations you've done before, like acetic acid, which is a weak acid, strong base. We expect the equivalence point to be basically in that like 8.6-ish range, probably in that ballpark. And that's usually also why when you use that indicator, they yell at you that you want the lightest color pink that basically persists. And that's because, again, if you kind of go to the lightest color pink, you're probably in this area here, which is most likely closer to the equivalence point. Again, as we talked about, if you're really super dark pink, you might have really jumped past the equivalence point, or not if you're not really being careful. But that's usually why we go for light color pink. We used a couple of different indicators the other day, I think, in that titration, right? And one really turned more in the sort of acidic range, right? And it went from sort of, I think, yellow to like a bluish sort of color. And then, in that sort of basic range, that's where the phenolphthalein would pick up. So again, sometimes we think phenolphthalein is like the indicator to use in all situations, but it's really not. And you would want to obviously pick one that's appropriate. So if we looked at something like this and we have this sort of list, which indicators would be good to use in this particular titration, HNO2 and KOH. Again, what you would want to look at is HNO2 is not nitric acid, but it's nitrous acid, which is actually a weak acid. And obviously KOH is a strong base. So if we have this titration, our equivalence point should be acidic, basic, or neutral. Yeah, our equivalence point here should actually be basic. Again, it's going to form nitrite, which is going to react with water, and is going to accept the H plus and make nitrous acid plus a little hydroxide. So at the equivalence point, that's essentially what we got going on. We have the formation really of a base. So we would expect some type of basic pH range would be good for us. That essentially really eliminates pretty much all these guys. You may be saying, well, isn't 7.6 sort of basic? And it is, but by the time that guy sort of turns 7.6, you know, it's already going to stay that color for the rest of the journey there. So probably not going to be your best one. This gives you a little bit more room in terms of things moving in the basic range and changing color. And obviously phenolphthalein would be a good choice. So these last two here would probably be your best choice off of this table for this type of titration, as you have some distinct, hopefully, color change that would occur within the basic range. You could actually do some theoretical calculations if you're doing a titration and really narrow in on which one would maybe be more appropriate. Again, if you know the molarity of what you're starting with of the acid and the base, you could just do a simple sort of titration problem and get a theoretical pH. And again, you could kind of go to your list of indicators and go, okay, this one definitely is going to show us, you know, the color change around the equivalence point. And that's obviously what you would be looking for, is definitely a color change around the equivalence point to indicate that you basically have reached the end of the titration. Any questions on indicators? All right, well, that wraps up this chapter here. Yes, sir. This list? No. No, so again, if this list was given to you and you're asked to pick an appropriate one like we're doing here, you know, you would need to pick the appropriate one and reason out why you would obviously pick that one. Other questions? Here, and we're going to talk about KSP and KF. And this is, again, we're on the back end of the hill here of, you know, really conceptual sort of information. So KSP and KF are a couple more equilibrium constants that we're going to talk about. We're going to start with really the KSP. KSP actually stands for solubility product. That's what the K basically stands for. And our KSP is really an equilibrium constant for things that are typically insoluble. So these are things that, if you remember your solubility rules, maybe. If not, if you think of solubility rules and those things that are typically, when we think about them being insoluble, these are really what KSP values are really for. Now, although, you know, when we learned about solubility rules, you know, sometimes people think, you know, it is always going to make a solid every situation that occurs. You know, so if we had something, say, like silver and chloride, for example, based on solubility rules, it says it's insoluble, which a lot of times we think of them as being 100% of the time that is the case. As we'll talk about in this chapter, there's a lot of things that really do affect solubility. And even though technically speaking, based on solubility rules, it may say that this thing is insoluble, there's factors, as we'll talk about, like the concentration of the ions, the pH of the solution, which really affects whether or not you would actually see that solid sort of form. Now, even if things are sort of insoluble, everything, even insoluble things, have a degree of solubility. It's going to be super, super small, going to break apart into ions, but it does have some degree of solubility. All KSP expressions are essentially written like this. You've got solid guy on the left and aqueous ions on the right. So that is 100% how all these sort of KSP reactions are written. And again, because they really are for things that are typically insoluble. So because it is an equilibrium, we can write an equilibrium constant, which is products over reactants, but pretty much because 100% of them have solid on the left-hand side, it essentially becomes just the products that we deal with in terms of the equilibrium expression. So that's why when we look at the KSP expression here, it is a concentration of silver times the concentration of chloride. And we still do everything that we normally would do. So we look at magnesium fluoride, because there is a 2 there, we still square it like we would do with a normal equilibrium coefficient. Here we have a 2 on the silver. So again, we square it there just like normal. We got a 3 and a 2. And, you know, we got both of those guys in there. So we still take, obviously, our coefficients as the exponents. And this is always how it's written, solids to aqueous ions. very important in this part of the lesson here is to understand how these ionic compounds break apart into ions. Yeah, so you could get the right sort of KSP expression and obviously do the calculations correctly. So it's really important to understand, you know, what ions they break into, how many you get, because it does affect obviously the KSP value. Now, when we look at KSP, because they are typically for insoluble things, KSP values are historically super small. And that makes really sense here because if we think about what a small K value means, it means we mainly have reactants or products at equilibrium if we have a small value of K. Small value of K means we have mainly reactants at equilibrium, which in every case, these reactions on the reactant side is solid, which means essentially it stays as a solid, but a little bit of it does break apart into ions. We'll see some really small values here, you know, minus 16, minus 30, you know, in terms of the equilibrium constant value here for it, and they're very, very small. We could also use something that we saw earlier on when we talked about equilibrium, which is another letter, which is Q, which is our reaction quotient. And remember that Q is pretty much calculated the same as, if I could write same as K, right? So it's still products over reactants. And same thing here, again, in a KSP situation, the reactants are going to be solid, so they're not going to be included. But, you know, before we sort of use Q to answer the question of, you know, are we at equilibrium and sort of which way we need to go to reach equilibrium, same sort of idea here. We use Q and compare it to the KSP to understand whether or not we would expect to have a precipitate form in a particular situation. So if we calculate Q and it's less than the KSP, and again, you could go opposite of where that's pointing to. So opposite would be pointing to the product side, and product side are aqueous ions, which means no solid. It would be an unsaturated solution, and we wouldn't expect really a precipitate to form. Unsaturated solution, right, means you can put more solid in there and it'll continue to dissolve, right? And it'll continue to dissolve until you hit a saturated solution. A saturated solution is one where you hit at a particular temperature the maximum amount of solute that will basically dissolve in that solution, or solvent really. And if you add more solid to it, it will not dissolve anymore and it will just keep piling up. So if you actually hit Q is equal to the KSP, you have a saturated solution, which a lot of people ask the question, would you see a precipitate or not? The answer is, well, you know, you might see a precipitate, but technically you're still at that point where enough of it will still dissolve, but you're pretty much right at the tipping point where if you add one more speck of it or something like that, you're going to start to see the solid kind of come out. So people sort of lean a little bit more towards you would see the precipitate. Technically, you got to kind of go over that equal sort of mark to see the precipitate occur. And that's what we see when we look at the Q is greater than the KSP, going opposite of where it points to, puts us back over on the solid side. And at that point, we have a supersaturated solution where we would expect a precipitate to form. A supersaturated solution is, again, one where you have technically way too much solute dissolved in that solution. It's an unstable solution, which means it doesn't like to keep that solid dissolved. It wants to basically release the solid back into the solution. And that's typically what happens with a supersaturated solution. And you'll definitely see, obviously, a solid that's formed. Any questions on that there? Here's a table clearly you can read, but you have one like this in your book. But if you look at a lot of these, again, a ton of them are very, very small values, and that's what we would expect because we are really talking about things that are typically insoluble. And again, it's basically going to stay on the reactant side, but we will still get a little bit of that equilibrium happening and a little bit of those ions basically going into solution. So when we deal with KSP problems, there's really two things that we deal with. One is what is referred to as the molar solubility, and that obviously is the molarity of this solution. Basically, it's how many moles of solute you could dissolve in 1 liter of a saturated solution. We oftentimes in sort of KSP will use a different letter as we're doing problems, and that is the letter S. And when we see S, it does stand for molar solubility. So when we kind of use S in calculations or solve for S, what we're solving for is really a lot of times the molar solubility, or really the molarity of it. But sometimes we want a more useful sort of version of it, and that is basically the solubility in grams per liter, right? And basically the main difference is if we want to go from moles to liters to grams per liter, what do we use to do that? We do use the molar mass to do that, right? The molar mass, grams per mole from the periodic table, right, will take us from moles per liter to how many grams you can dissolve per liter. So there's sort of two situations that occur with KSP problems. Really, one situation involves you having to, for sure, do an ice table. One situation, you don't necessarily have to do an ice table, but it can be very helpful for you to do one. And one situation is you're actually given the solubility of the compound. And what you would do is take that solubility of the compound either in grams per liter or moles per liter, and you would figure out what is the moles per liter of each of the ions that are present. And then you could go into the KSP expression and actually solve for what the value of the KSP is. The other type of problem is just a very simple problem, like what is the solubility of this compound? And really the only thing given to you is the KSP value, or you look up the KSP value for it, and you're not given any other piece of information. So typically speaking, you do an ice table in both, but you definitely got to do an ice table in this sort of calculation. And again, it may be helpful for you just to visually see everything. Do an ice table in the other situation, which you don't really need to. But again, there's a lot of places where you might have to, for example, add 3 and then cube it. And a lot of people go, wait, I already like added the 3 there. Do I need to still cube it, or do I need to cube it and not add the 3? So sometimes just doing the ice table, you can visually see, oh, I did the 3 and I also need to cube it. You know, it can be very helpful. So let's take a look at one here together and see how we can go through this. So the solubility of silver phosphate at 25 degrees is 1.6 times 10 to the minus 5. Here we are looking for what is the KSP for their silver phosphate. So this is a situation where we are looking for the KSP, which is technically a situation where you don't really need to do an ice table, but I'm going to do one here just to show you what it looks like and how it can be very helpful for you. So what we really want to do is start with an equation. And in these KSP problems, the equation is really the ionic compound breaking apart into its ions. So we would start with our silver phosphate here, which would be a solid. And by the way, I know it's a solid because it's a KSP I'm looking for. So that definitely tells me it's going to be insoluble. This is going to break apart into 3 silver ions plus 1 phosphate ion here. Now, in this problem here, if we kind of took an ice table approach, clearly, like normal, we're not going to really worry about, obviously, the solid part of it, right? So now I'm going to put any numbers. Now, here we're not given any numbers in this particular case, except for what the molar solubility is. So we're going to initially assume 0 here on both of these. Now the change part is going to be the same. We're going to assume it's going to the product side, which means obviously our left-hand side is going to be minuses, but they're solid, so we don't even have to worry about it, right? The right-hand side are going to be pluses, and here's where we use, again, a different symbol than X. We do use that S here in these tables. You could really use any letter you like, but very commonly people will use S's. And we still want to do the 3 like normal for the coefficient, plus 3S and plus S. That means at equilibrium, we have 3S here and S. So this is typically what a ice table will look like in a KSP problem. Again, it's very similar to ice tables that we've done before, except that we use a different letter. You could continue to use X if you like, it don't really matter, but most people will use S. And we can even do what we would normally do at this point, which is we would take our equilibrium, right, and put it into our KSP expression, our equilibrium expression, which in this particular case, the KSP would equal the concentration of silver, and we would cube it, right, because of the coefficient, and we would times it by the phosphate ion. And that means that essentially we're going to put in there 3s cubed times s. Now, earlier we talked about that the S here really does stand for molar solubility, right? And if we look at the question, it tells us that the solubility of this guy is 1.6 times 10 to the minus 5, which means that is the molar solubility, right? Moles per liter. And that number would go into here. And we would get 3 times 1.6 times 10 to the minus 5 cubed times our S, which is 1.6 times 10 to the minus 5 here. And if we did all that good stuff there, hopefully on this calculator, 1.6 exponent negative 5 times 3, we're then going to cube it. Try this. And then we're going to times it by 1.6 exponent minus 5. All right. So hopefully on this calculator, if it's right, we get a molar solubility of 1.8 times 10 to the minus 18, basically moles per liter. And if we wanted grams per liter, we could clearly use the molar mass of silver phosphate and figure out how many grams that would be per liter. Any questions on that? Now, I said you don't really need to do an ice table here if you understand molarity and concentration and how it works when you break apart into ions. So, and it's really what the ice table can do for you if you're not sure about that stuff. But when you look at obviously our silver phosphate, and when it breaks apart into our 3 silvers plus our 1 phosphate, and if this guy's concentration is 1.6 times 10 to the minus 5, it is a 1-to-3 relationship, right, between that and the silver, which means the concentration of the silver in that solution would be 3 times 1.6 times 10 to the minus 5, which is essentially what the ice table did for you right there. So you didn't screw up. When we look at silver phosphate to phosphate, it is a 1-to-1 relationship, which means the concentration of this guy is 1.6 times 10 to the minus 5, which is also what the ice table did for you if you really don't understand how molarity breaks apart. If you do, you could just take these numbers and go right into your KSP expression and be done with it without having to do the ice table. But again, if you do the ice table, it gives you those relationships of the whole thing to each of the ions in terms of the molarity and how they're related for you. And it might be a safer way of doing it. But technically speaking, you could just go to the concentration of each of the ions and then into the KSP expression. Obviously, you would get the same answer. Any questions on that there? Yeah. Yeah, you really shouldn't. There's a few cases later on when we kind of mix KSP with something else, but you know, in a true sort of just straight KSP problem, it really should be the solid on the left-hand side, which really means that when you're doing any type of ice table, you probably shouldn't have any numbers on that side. It all should be on the other side. Yeah. You should, and a lot of times what they do, the reason why they will sort of insert that in there is if you ever look at any of those sort of tables in books, most of the time the tables in the books are done at what they call standard conditions. And basically standard temperature conditions is like room temperature, 25 degrees Celsius. And if it's a pressure, it's 1 atmosphere. And if it's something to do with concentration, it's 1 molar. So that's why a lot of times in these problems, they will kind of throw the temperature in there just to tell you, you know, you could use pretty much the value you would find in that table. And it's really also because it ultimately is an equilibrium constant, right? And the one thing that we talked about that does affect the value of the equilibrium constant is temperature. And, you know, if it was some weird temperature, you know, most tables are 25 degrees, you would have to technically go find the correct K value for that particular temperature. Yep. But in most of these problems, really nothing to do with temperature in terms of the calculation part. Other questions? All right. Well, we will lay that up here for like, I don't know, like a week and a half, I suppose.